I want to talk to you about a new capability that we've added to DonkeyCar. As if you don't know DonkeyCar, let's go to the DonkeyCar site. If you don't know DonkeyCar, DonkeyCar is well known as the hello world of autonomous car frameworks. And what it does is it allows you to, it shows you how to modify an RC car, adding a Raspberry Pi, a camera. This is called a PCA 9685 board. It's for controlling the servo and the motor. And you can put these things together, and then what the DonkeyCar software will let you do is drive around a track and gather data with the camera, and then take that and use that data to calculate a neural network that then can be used to drive the car around the track autonomously. So this works really well indoors because the lighting conditions are well controlled indoors, and we're using a pretty cheap camera here, like $20-$25 camera. Is very susceptible to changes in lighting conditions, but indoors lighting conditions are fairly controlled. We use this to race in races sponsored by, but organized by DIYRobocars.com organization, which is a grassroots organization to promote autonomous technology. And so we do a lot of fun indoor races with this, but more recently DIY Robocars has started doing outdoor races. And unfortunately, DonkeyCar is not as good for outdoor races in its current state. It's not as good for outdoor races. Again, because of this camera thing and lighting conditions, you can't control them outdoors. Lighting conditions change from day to day. They change over the course of a day. Shadows matter, so it's not that great for outdoors. So what most people have been doing outdoors is they've been using GPS, because now you have the sky available to you and you can talk to GPS satellites. So let's talk a little bit about, so here's a version of the DonkeyCar that's set up to use GPS. And you can see there's no camera on this at all. It has a GPS receiver, GPS antenna, and all the other stuff that DonkeyCar has, the Raspberry Pi, the PCA 9685, that kind of thing. But the new things are the GPS and the GPS antenna. So it's worth talking about how GPS works just in a very simple way, so we can understand how we pick which GPS receivers to work with and how to organize the software to use them. So GPS really there are we think of GPS as one system, but really GPS, the Global Positioning System, is the first version. It's the American version, but there's a Chinese version for global navigation called Baidu. There's a Russian system called GLONASS, and there's a European system, and I can't remember the name of the European system. Okay, but there's sort of four major satellite systems that provide global positioning. I'll just refer to them as GPS, just generally, just because that's easier. So we have these satellites in geosynchronous orbits. So they're at a fixed location above one part of the Earth, and they know what that position is, and they have very precise timing information, and they're constantly broadcasting their position and their time, the current time. And so when you receive it on the face of the Earth, and you have very precise timing, now you can take the time difference using the speed of light. You can calculate how far away that satellite is. So the satellite told you where it is. Now you know how far away from you it is, and you can use a bunch of those satellites and triangulate your location on the face of the Earth. And that's essentially what a GPS receiver does. So let's talk about GPS receivers, because GPS receivers range all the way from like $10 to several $100s, and there's important differences. So a 10, the ones that we commonly use. Well, let's actually talk about those $10 ones. So the $10 ones, there's a company called U-Blocks that makes that makes these chipsets, and there's more than one company that does it, but we tend to stick with U-Blocks. The $10 ones tend to use U-Blocks Series 6 and Series 7, and the Chinese knockoffs and other companies sort of low-end chips. And but then U-Blocks also has a Series 8 chip, and that's better than the Series 6 or Series 7 chips. And they also have a Series 9 and Series 10. Series 10 is sort of not really available for us as hobbyists yet, but Series 9 is. And Series 9 is considerably better than anything that came before it. So I'm going to just talk about Series 9 because it's available now and it's better than anything that came before it. So as an example, here's a board made with the U-Blocks Neo M9N chipset. So they have these really great names. And it's about $75. It has USB-C for you to connect it and get it power and get it talking to your Raspberry Pi. It has an antenna connector to use an external antenna, and you're going to want to use an external antenna. That'll help you with your accuracy. The SparkFun boards also have this nice thing where they have this 4-pin quick connector that it serves as an I2C bus, so you can actually talk to this chip via I2C if you wanted to, if you needed extra sort of ways to communicate to it. So this is a $75 board. It talks to all four of those systems. I believe it can talk to them all four simultaneously if you're going at a low enough rate. And once you start to increase the rate, then it starts to drop off satellite systems, so it doesn't have to do as much work communicating with them because it has to do more work trying to get you more estimates. And it uses a single frequency. And we'll talk about in a little bit why one or two frequencies matter. So that's a $75 board. This is the board I actually used when I created this DonkeyCar that we'll be talking about. And this is also a Series 9 chip, but it also implements a thing called RTK GPS, real-time kinematics GPS, and that dramatically improves the accuracy. It also dramatically increases the price. This board, I paid $275 for the board. This uses two frequencies, so you need what's called an L1, L2 antenna to take advantage of that. That is also more expensive. I think I paid $75 for the antenna, so that's like $350 so far. But what you get for that is very, very precise positioning estimates. And it isn't, I showed two SparkFun boards, but anybody can use the U-Blocks chips to create a board. And so there are other ways to get a good U-Blocks board. You don't have to go through SparkFun. This company, Argue Simple, actually uses the exact same chip as this one, but this board, instead of being $275 plus you have to buy an antenna, this board here is $232, and it includes that L1, L2 antenna. So whereas my setup with the SparkFun and the L1 and 2 antenna costs $350, this is going to be, $235 plus whatever shipping is. So you can get in cheaper than I got in. I actually just bought one of these, so I'll do an unboxing and I'll set it up so it can work with DonkeyCar, and I'll have a separate video on that. So those are the receivers. So how accurate is GPS? Okay, well, that depends. That depends on what kind of a receiver you're using and the conditions under which you use it. So let's talk about those cheap receivers just for a second. The $10 ones. So those might be based on a U-Blocks Series 6 or Series 7 chip or a Chinese clone of those chips. And, like 10 or 15 bucks for GPS. And I wrote, as part of this project to allow DonkeyCar to use GPS, I wrote a GPS driver, and as part of that driver, I wrote a little main program where you can have it record points over time, GPS points over time. And I used that with one of these cheap ones, and I recorded one position per second for 100 positions. And I left the GPS stationary, and this is how it came out. So this represents the meters here. So you can see that even though it's really stationary, the position looks like it's changing over time. And this axis is 9 meters or something like that, and this axis is 5 meters. And as you can see, it looks like it's a walk. It looks like it started here, maybe it started at the other end, but it looks like it started here and sort of walked along here. So what's that all about? Well, let's go back to the way GPS works. GPS talks to these satellites, and these satellites have an idea of their position, and then they send you the position and precise timing information so you can calculate the distance. Well, that radio signal passes through the atmosphere. There's two kinds of errors, major kinds of errors that sort of creep into this, and none of them are random. So if you look at this isn't like a bunch of random points around the center. It's not Gaussian noise, right? It's changing over time, but in a not in a random way. So the reason it's not random is that much of this error comes from two sources. So one is this notion that the satellite knows its exact position. Well, its orbit has perturbations in it. It's not a perfect mathematical orbit because there's other bodies that are influencing its orbit beyond the Earth, and even the Earth itself, the Earth's gravitational field is not completely uniform. So as its orbit changes, its idea of where it isn't exactly correct. And so and that perturbations change over time, so that's part of this changing over time thing. The other thing is that it sends that position and timing information via radio signals, and those radio signals have to travel through the ionosphere and the atmosphere to get to you. And the ionosphere and the atmosphere change over time, and that also adds some error. And so that's why this thing looks like it walks. And one way, there's a couple ways to mitigate these errors, to reduce these errors. So one is talk to more satellites. The more satellites you can talk to, then the less any given satellite's error is going to affect the overall estimation. And so if you move up from the Series 6 or Series 7 to Series 8, it can talk to more satellites simultaneously. More satellite systems and more satellites simultaneously. And so this is an example of a u-blox Neo M8N based GPS receiver. Again, sitting stationary, and here I've recorded 1,000 points, so 1,000 seconds, 1 per second. And here you can see the delta here is about 5 meters this way and about 5 meters this way. So that's better than it was before. Not a lot better, but it is better. But we can do a lot better than that. If you go to a 9 series chip, here I did the same thing here with the ZF9P chip. It's stationary, and I recorded 1,000 points, 1 per second. And then over that period of time, you can see that the delta is only about a meter, a little over a meter in that direction, a little over 2 meters in this direction. That's substantially better than the 8 series chip. So the 9 series chip is better, and this represents that board that's about $75. So the question is this good enough for racing? And unfortunately, again, the answer is maybe. So let's just say that the track you're going around, you can get around that track in 20 seconds. So let's figure out sort of what's the maximum amount of drift that may occur over one lap. So we're taking these once every second. So let's start at one that starts at 8.25 here, like this one, and let's count off 20. It's 5, 10, 15, 20. So here we are here at about maybe 8.85 from 8.25, so that's about 0.6 meters, and you can see that the vertical one hardly changed at all, or maybe less than that. So let's use the bigger number, 0.6 meters. So over the course of a lap, your GPS position may drift 0.6 meters. Well, if you're start in the middle of the start line, so you're in the middle of your track, and your track's 2 meters wide, so a meter on either side of you, and you're only going one lap, 0.6 meters means you'll still be on the track by the time you cross the finish line after one lap. So that's maybe good enough for a one lap race. Now, if your lap is a lot longer than that, or if you have to race multiple laps, then the drift, this is enough drift, like it's 2 meters on one side. It's enough drift that you may drift off the track while you're racing. So can we do better than this? And the answer is yes. You can get an order of magnitude or two better than this. So this is like 2 meters, right? Plus or minus 1 meter. You can get like 2 meters, 2 centimeters of accuracy using what's called RTK GPS. So how does that work? Well, RTK GPS, it has a regular receiver, that'll talk to a lot of satellites. But beyond that, it takes a second source of data called corrections. So the way it works is that there's base stations in the world that are well located. They know where they are precisely on the surface of the Earth. And they can then talk to the satellites and get an estimate based on the current state of the satellites about where they are. And there'll be some error in that, right? So we already saw here, let's say the base station really knows it's really right here. But then it talks to the satellites, and the satellites say, you're over here. Well, now it has a delta. It has these two deltas, right? And it can subtract them from what the satellite says, and now it's back to where it is. And now it can send that correction out so other people can use it. And sort of that's at a very high level and a simplistic level, that's how it works. But who can use it? Well, remember how this walking thing, there's two things that affect it. So one is perturbations in the satellite's orbits. So if this is caused by perturbation in the satellite's orbit, this error, you want to be looking at the same satellites with the same perturbations, because when you subtract out those perturbations from your value, from your position, you want them to be the same errors as the base station is seeing, right? So you want to be talking to the same satellites. The other thing is the other errors that creep in, the drift that creeps in, is atmospheric conditions, ionospheric and atmospheric conditions. So you want your radio signals to be passing through the same set of conditions as the base station. So the best way to do both of those things is to have the base station really close to you. And so one way to do this, and let's go look back. Let's look at the car that I have. I'm going to show you the DonkeyCar that I set up. Okay, so here's that U-Blocks chip. Here's the cable to the antenna. This is a L1, L2 antenna. I'll talk about that. And this is a base plate to make sure the antenna, it gives it electrical ground so the antenna's good. And so we want to get, this thing can talk to the satellites because it has radios in it, but it needs the corrections. How do we get to the corrections? Well, there's two ways to get corrections. So one way is to have another one of these and another base plate and another antenna. And you set up your own base station doing that. And so your base station gets well known where it is, and then it can calculate corrections. And then you attach a radio to the serial port on one of these on one set of these pins. And so your base station broadcasts the corrections, and your rover, the one that's moving around on your car, that one receives the corrections. So that's one way to do it. You can get a second setup and treat it as a base station. Of course, that doubles your price. Now you're going from where I paid $350 for this stuff. Now you're $700. So the other way to get corrections is you can get them over the internet. And there are government organizations, there are universities, and there are professional organizations that maintain networks of base stations that have very well localized the position of that base station. And they'll talk to the satellites and get corrections, and then they'll broadcast those over the internet using a protocol called N-trip. And the corrections format themselves is called RTCM. So they'll broadcast RTCM corrections over the internet using the N-trip protocol. And so let's talk about how to get those. Please correct me. Yeah, so I use an organization called UNAVCO, and UNAVCO has servers, a lot of servers all over the place, but in particular they have three base stations near me, near my home. They have a base station also near Oakland where we race outside there, and they have a base station very close to the track in Fremont where we go there. But you can see this is their network of base stations. So if you're near one of these, and what does near mean? Near means, some people say within 15 kilometers. The documentation actually says within 30 kilometers. And again, it's because you want to be seeing the same set of satellites, and you want to be experiencing the same set of atmospheric conditions. So the closer you are to a base station, the better. But outside of 30 kilometers, it's said to not be useful. So that's UNAVCO. You can, if you're someplace other than North America, there's this site called rtcm-ntrip.org. And they have a list of organizations all around the world that provide corrections via the N-trip protocol. So you can go to that website and see if there's an organization that has base stations near you. And basically what you do, most of these are free, right? So you go to their website, you sign up for an account, and then you get credentials, and then you can sign into their servers and start getting the corrections from their servers. And then there's another organization called RTK2Go, where some people have, they bought their receiver, and they bought their receiver, and they have their setup, and they can set it up as a base station, sort of the reverse of what I'm doing, which is they can set up their computer or Raspberry Pi or whatever to broadcast the corrections that they calculate. So RTK2Go is an organization where you can figure out if there's anybody broadcasting near you, so you can use their corrections. You need to install some software to make that work. I'll talk a little bit about the kinds of software that you can use. But let's first talk a little bit about the hardware piece again. Okay, so now if you're getting corrections over the internet, so in my setup, when I'm at home and I'm driving in my driveway or in my backyard, then my Wi-Fi reaches out there. So I can just set up my Raspberry Pi to talk to my Wi-Fi and get corrections from my UNAVCO server. And then I route those connections out this USB serial port into the USB serial port of the receiver. And that's how it gets corrections. Now I still need to read the positions. GPS sends out data. The GPS receiver sends out data as what's called NMEA sentences. So I need to read the NMEA sentences. And I do that via a second serial port. So I soldered pins onto this board, and I use its serial port, and then I connect that to another serial port I have exposed here on the Raspberry Pi, and that's how I read the NMEA sentences. So if you're using RTK, you need two serial ports, one to send the corrections to the receiver and one to read the actual NMEA NMEA sentences from the receiver. If you're using the cheaper one where you're not getting corrections, then you just need the USB serial port or some other hardware serial port. You need a single serial port. Or like I said, in the case of these SparkFun ones, you can actually use the I2C port to talk I2C to it. But you just need one source to read the NMEA sentences. Okay, so so the software to actually do that. So the first one I want to talk about is this uCenter software. So this is, let me see if I have a picture of it here. I think I do. Yeah. So uCenter is a piece of software that uBlocks has written to configure their chipsets. And that's why I tend to only talk about uBlocks, because this piece of software is very useful. It allows you to configure a whole bunch of things to optimize your GPS receiver in terms of how often you can make a trade-off between how often it will send out a GPS estimate, position estimate, versus how accurate that estimate is. Because the more satellites it's talking to, the better the estimate will be. But if it's talking to more satellites, it has to coordinate all that information, and it can't send it out as often. So talking to less satellites means you can get updates faster, but those updates won't necessarily be as accurate. So you have to experiment with your particular setup to decide what that trade-off is. But the thing is, you get to make that trade-off if you use this uCenter software. So that's uCenter. That's to configure your chipset. Now, to get, how do we get if you're going to get corrections over the internet, how do you do that? So there's two different ways, two different pieces of software that I've tried. So the one that I actually use is this thing called RTKlib. And RTKlib is a set of C code that you compile on your Raspberry Pi, and it will go talk to your N-trip server and go get those corrections, and then let you route them to different places. So for me, I have when I run the RTKlib software, it goes to my UNAVCO server, and then I route them out the USB serial port, and so they end up in the serial port here. So I set up RTKlib to do it that way. Another way to do it is with the Ferber N-trip client for Android. So it's at this point it's worth talking about where your Wi-Fi is coming from. So remember I talked about in my driveway I can just get my Wi-Fi, but what if I'm at a racetrack? Well, if I'm at a racetrack, the racetrack in Fremont doesn't have Wi-Fi. So how do I get an internet connection? Well, the way I've chosen to do it is, the way I've chosen to do it is to add a little place to stash my phone on the car. So I added this platform below this one, and I wrap my car in this foam so it's it's not vibrating and it's safe in a crash. And now I can set the phone up in Wi-Fi hotspot mode, and now the phone is getting the internet through its mobile connection and rebroadcasting that as Wi-Fi, and then I have my Raspberry Pi paired to its Wi-Fi, and now I have internet, and because it's attached to the car, I have internet any place this thing drives, and it worked really great. So now I have the internet on the Raspberry Pi, and now I can do that whole use RTKlib to talk to the servers and route everything. So that's one way to do it. Now another way to do it with your phone is with this Ferber N-trip client for Android. So now instead of the software that talks to the server running on your Raspberry Pi like RTKlib does, now you use this N-trip client for Android, and it's your phone that's directly talking to the N-trip server, and then it can rebroadcast that over Bluetooth, and then you would have your your Raspberry Pi pair to your phone's Bluetooth, and now you're getting the corrections that way. And again, you can route them any way you want. So that's another way to do it. And this is for Android, so if you have an iPhone, that's probably not going to work, and you're going to end up using RTKlib on your Raspberry Pi. I haven't tried RTKlib, or did I try RTKlib on a Jetson Nano, but I believe it'll work just fine too. It's a very simple C program. And then, of course, I'm using DonkeyCar, so you need the DonkeyCar software, and in particular, you need a particular branch of DonkeyCar right now. And I'll talk about that in just a second. I did have, because I needed 2 serial ports, I did have an issue with setting up this solution on my Raspberry Pi, because I needed this second hardware serial port. I needed the second serial port. So I used the USB, and there is a default serial port exposed on the, I think, pins 7 and 8 on the GPIO of the Raspberry Pi. The problem is that didn't work well for me, and I'm not positive why. But one, it's a software UART. It's not hardware, so it's software based, and I think it's used for logging in as well. So there might be another process listening to that one. So, but one of the things about the Raspberry Pi 4 is it actually has 6 hardware UARTs. One of them is used for USB, but the 5 of them aren't used at all. So you can map those to the GPIO. So I mapped hardware UART 3 to a couple of pins on this GPIO bus, and then I started using that, and that worked great. So if you have a Raspberry Pi 4, and I talk about that in this article that'll be linked to this video, but I talk about that in the article about how to set up that hardware serial port and which pins it gets exposed on. But once you do that, then the second serial port works really well. I couldn't get it to work. Honestly, I couldn't get the solution to work on the Jetson Nano for that very same reason. The UART on the GPIO bus was not reliable, so I didn't really have a second serial port to use the Jetson on, to use this RTK solution with Jetson. Okay, so what do we use this for? Well, we race with it. We race outdoors. So DIY Robocars have started doing these outdoor races. So I actually got this thing working a couple of days before the July DIY Robocars outdoor race. So that was the first race I used in it. And again, I set it up so my phone is carrying around the phone, is getting RTK corrections. Fremont has one just a couple of kilometers, a UNAVCO N-Trip base station just a couple of kilometers away from the race course. So that part all worked great. And then the race itself was pretty interesting because there were a bunch of people showed up, but only 4 cars were ready to actually race. And it was interesting because all 4 of those cars used a different technology stack to do this, right? So they're all using GPS, but they're all using different software stacks. But that was kind of fun. Unfortunately, one of the competitors crashed out and broke their car in a warm-up run. So we only had the 3 cars to actually do the race. And one of those cars, this is the DonkeyCar that I showed you. That's my car. So that's running the DonkeyCar branch that I'm going to point you to. This car here is a much larger car, and it's running ROS, like an F110th. If you know F110th, they have a ROS-based stack for that's sort of similar to DonkeyCar, but much more complex. So that's running F110th ROS. This car here is working with another open source software stack called RG Rover, and it's running a Pixhawk controller. So the Pixhawk and RG Rover are open source software, and the Pixhawk is well known as being a flight controller for aerial drones, right? For it's open source software that a lot of people use for aerial drones, for flying their drones around and having them go through GPS waypoints and things like that. RG Rover is open source software that uses that, and it's actually commonly used on agricultural equipment to drive them around in fields for plowing and everything. And here it's being used to race a race car. So that's pretty cool. I will link to this video. I'm going to play it in this context right now. And so the quality won't be great because I'm recording a recording. But you get the idea. You'll get the idea. So again, this is the DonkeyCar. This is RG Rover. And this is Ross. I got off early.
The truck didn't go.
I got passed by Pixhawk, RG Rover. Got passed again. But here comes Ross from behind. It's going really fast.
He gave him a head start.
Oh man. So he turned me all the way around. And it keeps going. And look, I kept going there. I actually finished the lap. It recovered and finished the lap. The Pixhawk car. Oh, that was horrible. So the Pixhawk car got completely wiped out. So it wasn't able to finish. But I ended up actually finishing. So I thought that was kind of cool that even though it got turned around 180 degrees, that it was able to recover and finish the lap. At that point, I took it out of the race because I didn't want to get it crashed again. But it survived. It worked great. So if you want to use DonkeyCar outside with GPS, how do you do that? Well, right now, I would recommend that you use this branch here. It's called 921 GPS Logger. This is the branch I used in that race. And the way that the software interface works is similar to the way standard DonkeyCar works in that it's in phases. So you say, I want to record, and you say, I'm at the origin, start recording, and then you drive once around the track and it records waypoints. And then when you're done, you save those waypoints, and then when you want to race, you say, I'm at the origin again, go. And then it follows those waypoints. So there's this recording stage and then the autopilot stage. And that's all in this 921 GPS Logger branch. Now we are in the process of merging this into main, so it will become a part of standard DonkeyCar. You won't have to use a branch, but it's a lot of changes, and it will take a little while. And you'll know when that's done because this branch here will no longer exist. If you go to this branch and it's not there anymore, use main because we've finished merging it. We're going to do it in several steps, so that the changes that we actually merge in are small enough to be testable. So I hope that you do try using GPS with DonkeyCar. I'm not the only one that's used it so far. Tom is one of the maintainers, and he's used that $75 GPS with a robot that he has, and he's had success with that. So I hope you give it a try. And thank you for listening. Bye-bye.